Hey guys, this is CHEMPLIFIED and today we will talk about non-ideal solutions. In our previous video, we already talked about ideal solutions. In this video, we will talk about non-ideal solutions and about non-ideal solutions which shows positive deviation from Raoult's law. Right? In the next video, we will talk about those non-ideal solutions which shows negative deviation from Raoult's law. So let's start. Now, first of all, what is the meaning of non-ideal solution? Non-ideal solutions are those in which AA interaction or BB interaction is not equal to AB interaction. Means when the solution is present in pure state, that is only A component is present, their interaction, I repeat, whenever I say the term interaction, I am talking about force of attraction between the particles. So in our first case, the force of attraction between AA and force of attraction between BB is not equal to the force of attraction between AB. That is in our solution. AB means solution. We have already mixed the two components. In ideal solution, all these three interactions were equal. But in non-ideal solution, these three are not equal. Now, how to define non-ideal solution? Those solutions which do not obey Raoult's law are called non-ideal solution. For such solutions, partial pressure of component A, we are talking about a solution of two liquids only, A and B. Right? Our solution consists of component A and component B. Now, for such solution, partial pressure of A is not equal to vapor pressure in pure component multiplied by mole fraction of A, and partial pressure of B is also not equal to pure component vapor pressure multiplied by mole fraction. This is our Raoult's law. Yes, this was the statement for Raoult's law and this was the formula given for Raoult's law. Now, non-ideal solutions are formed when components differ in their structure and polarities. Polarities means whether they are polar or non-polar in nature, right? Non-ideal solution either show positive or negative deviation. These all statements were for non-ideal solution, and this particular statement is the definition for non-ideal solutions. Others just define or describe non-ideal solution properties. Now, our last statement is non-ideal solution show either positive or negative deviation from Raoult's law. In today's video, we will talk about those non-ideal solutions which shows positive deviation from Raoult's law, right? So this is the graph that we have already seen in our previous video for ideal solution. Now remember the white line represents the graph of ideal solution and the yellow line represents the graph of non-ideal solution. So in this case, let's write the values. PA is greater than, partial pressure of A is greater than mole fraction of A, and P naught A. Second one, partial pressure of B is also greater than P naught B, mole fraction of B, and total pressure of the solution or P total is also greater than P naught A mole fraction A plus P naught B mole fraction B. We can write it as PA plus PB. That's how you understand the graph. Now, the real problem is why partial pressure of A is greater, why partial pressure of B is greater than the calculated value, why it is happening, why the total pressure is greater than the calculated value from Raoult's law, right? Let me put the arrow. Now, I repeat a few more things. At this particular point, mole fraction of A is 0, which means only component B is present. So when only B is present, the vapor pressure at this particular point is P naught B. That is vapor pressure in pure state. Now look at this side. Here mole fraction of B is 0, means only A is present. So this At this point, the pressure is P naught A, that is vapor pressure in pure state of A. So this is the graph for non-ideal solution which shows positive deviation. Now according to Raoult's law, the graph should follow the pattern followed by the white lines. But in our first case, we are having positive deviation. It means when we mix the two liquids, the solution shows positive deviation, that is elevated value of both vapor pressure as well as mole fraction. Right? Now why this is happening, we will talk about this. Now if you read the characteristics, you will find that in these solutions AB interactions are less than AA and BB interactions. What do you establish from this statement, that AB interactions are less than AA and BB? Now, whenever I am talking about interactions, I am talking about force of attraction between the particles. Now, AB interactions are less means force of attraction between A and B. Force of attraction between A and B is less than AA and BB molecular interaction. Let us consider a simple example by drawing. Look at the first diagram. The first diagram shows that the container consists of only component A. Now I have already told you that AA interaction is greater than AB interaction, which means the particles of A are close together. They have some force of attraction between them, which because of which they want to be together with each other. Right? Same goes for B. If I put B in place of A, I will also find that BB interaction is greater, which means particles of B also want to remain close together, right? But as soon as you mix them in a solution, in our second diagram, as soon as you mix them in solution, the interaction of A and B is not good. They don't want to be close together. There is no good force of attraction between them. What happens because of that? What is happening because of that? They are far from each other. They don't want to come close to each other, due to which the characteristic of volatile behavior increases and vapor pressure increases, which means the total pressure is greater than the pressure shown by the Raoult's law. Understood? Since there is no interaction, the solutions become volatile and the total pressure increases. Right? Why? Because interaction or the force of attraction force of attraction between A and B is not good. So the solution becomes a little bit more volatile and the pressure above the liquid increases. Right? Now, let's go to the second statement. The total vapor pressure of the solution will be greater than the corresponding vapor pressure expected in case of ideal solution. That's what I have told you. Since the interaction is low, the volatile behavior increases and pressure increases above the liquid. In simple terms, the solution is not stable. Since the solution is not stable, the particles don't want to come close to each other, they want to go away from each other, which increases the volatile behavior, and the particles try to escape from the solution and go out in the vapor. Right? So the pressure increases. The pressure is because of vapors of the components, that is A and B. Right? That's why the total pressure is greater than the pressure calculated by Raoult's law. Right? We will talk about these terms, but first let me remove the diagrams. Now be prepared. Now we will talk about the most important terms, delta H and delta V. Delta H and delta V. First we will talk about delta H, that is enthalpy of mixing. When you mix two different components together, in our case non-ideal solution, delta H mixing is greater than 0. What is the meaning of delta H mixing greater than 0? It means that the process of mixing the two components A and B in this case is endothermic. What is the meaning of endothermic? Energy is absorbed. Energy is absorbed. Why this is happening? In this case, why energy is absorbed? Let's try to understand that. Now, consider the example, our previous example. Let me draw the diagram first. Now, before we talk about delta H mixing, remember that AA interaction and BB interaction is greater than AB interaction. Just remember this statement, right? Now, come back to our diagrams. Let's come back to our diagrams. You have already seen these two diagrams. Now, consider the case of component A. Since the force of attraction between the particles of A is greater, the particles will remain close together. What is the meaning of close together? By the term close together, I mean to say that they occupy less volume, right? They occupy less volume. And by the meaning of close together means they have greater force of attraction between themselves. Same goes for A and B. We have only taken the example of A, but we can also say this for B, component B. Now, since the force of attraction is higher, and when you mix them in the solution, the interaction of A and B is less, which means you have to break the bond. You have to break the bond between AA. You have to break the bond between AA so that a new bond can be formed between A and B. Now, to break this bond between AA and BB, some energy must be provided. Some energy must be given to these components so that the bond can be broken. That's why the delta H mixing is endothermic. I hope you get the point. To break the bonds between component AA and component BB, some energy must be provided. That's why delta H mixing is greater than 0. Also, the bond found between A and B is weak, right? Is weak because it is found by providing energy. No energy is released in the formation of bond A and B. Now we will talk about why delta V is greater than 0, right? Now, what is the meaning of delta H? Change in enthalpy. The change in enthalpy is greater than 0 because energy is provided. Now, let's come back to volume. Delta V mixing is greater than 0. What is the meaning of delta V mixing? When you mix the two components, the volume of the solution increases. The volume of the solution increasing. I am not talking about pressure. The volume of the solution itself increases. How is this possible? Why the volume of the solution is increasing? Let's talk about that. Now, in the first diagram, we have component A. Now, since the force of attraction between component A is greater, the particles will remain close to each other. What is the meaning of close to each other? It means they will occupy less volume. Right? Now, as soon as you mix them, now look at the distance between particle A and particle B. The particle A and particle B. Look at the distance between particle A and particle B. It is greater. It has become large, which means they will occupy larger volume. Even if the change in volume is very little, but still the change is there, and a positive change because the volume increases. That's why delta V, or change in volume while mixing the components A and B, is greater than 0. Remember that. I hope I made you understood why delta H and delta V are greater than 0 in case of non-ideal solution, which shows positive deviation from Raoult's law, right? Now, delta S mixing and delta G mixing is positive and negative. We have already talked about this, that these two values will never change for ideal solution as well as for non-ideal solution. Why entropy will not change? Because in both the cases randomness is increasing, number of particles is increasing, and delta G is negative. Why? Because all the processes are spontaneous, and for a process to be spontaneous, delta G is always negative. The only values that will change is delta H and delta V. In ideal solution, delta H was equal to 0, delta V was equal to 0, but in this case, in positive deviation, delta H is greater than 0, delta V is greater than 0, right? Before we move ahead, let's talk about total pressure. Why total pressure is increasing? Now, in simple terms, if pressure is increasing, it means more components, it means higher number of components are moving from liquid to vapor phase, right? If pressure is increasing means more components are moving from liquid to vapor phase. Why this is happening? Because we already talked about delta H and delta V, so we know that the components A and B in the solution have interaction less than the interaction of less than the interaction of AA and BB. Because of this less interaction, the volume of the solution increases, the volatile behavior of the solution increases, and more if the solution is volatile, it will provide more vapors from the solution at a constant temperature. That's why total pressure is greater than the pressure calculated by Raoult's law. That's why this solution is a non-ideal solution, right? Now these are the examples of those liquids which shows positive deviation from Raoult's law. You can pause the video and look, just check them out. These are the examples. This will be it for today's video. Thank you very much for watching. Have a nice day.